Hi, and welcome to Dr. V's Chemistry webcast. Today we're talking about classification of matter at kind of introductory level for maybe first year chemistry students. What we're going to talk about in this webcast are atoms, molecules, pure substances, mixtures, different types of mixtures, fairly low key, introducing some particle level representations of this and just trying to get you starting to understand what we're doing here. So to backtrack a little bit, we're talking about chemistry, right? We're in a chemistry course, and chemists are very concerned with what materials are made out of, what's their composition, and how do they react or how do they change when they're introduced to other materials, right? So composition and changes. What's it made out of? How does it react? This is what chemists care about. Right? There are a lot of different branches of chemistry. So I trained as a physical chemist, where we were interested in why do these things happen. The organic chemists want to know what can they make carbon and carbon molecules do. The analytical chemists want to know how can I figure out what stuff is made out of. There's a lot of different branches. Oh, geochemistry, medicinal chemistry, so many different things, and it's all really, really interesting. All matter has a chemical basis. Don't be fooled by the ads you see on social media. Oh, well, this is a chemical-free substance to help you sleep better. It's not chemical-free. It's made with chemicals. All matter is made out of chemicals, right? Water is a chemical. Your body is a whole bunch of different chemicals all mixed together. Anything that has mass or volume has a chemical basis. Don't be fooled, all right? You know better, all right? Now, what we know is that all matter is made up of atoms. The smallest building blocks are what we call atoms. They're the smallest pieces of the different kinds of elements. So on a particle level, we might represent them as little circles, right? Each element has its own kind of atom and its own symbol in the periodic table. And we can put them together and make all kinds of interesting things. So when we talk about a substance, we mean it's a particular kind of matter where what it's made out of stays the same and is constant no matter how you got the sample. All right. We could have gold. We could have diamond. We could have sugar cubes. These are substances. All right. So sometimes you'll hear the term pure substance. We don't really need to say pure. The term substance in a chemistry context really implies that there's only one kind of material present. All right. So a hallmark of a substance is that it can be represented by a single chemical formula. So our gold bars, the symbol for gold is Au. Our diamond is carbon. I can just write carbon. That's what it's made out of. My sugar cubes here are made out of sucrose, C12H22O11. And we're saying that's all that's in there. The gold bars are all gold. The diamond, we're hoping, is all carbon. The sugar is all sucrose and nothing else. All right, so we can say that they're pure. Those are the only things present. All the pieces are the same. Molecules are clusters of atoms that behave as a unit because they're chemically joined. Now, it's not my intent today to talk about the nature of the chemical bond. That's not what I want to do. But they behave as a unit. They stay together, right? And so we can have some depictions of molecules where we have some white atoms and some red atoms and some yellow atoms stuck together, and they stay together. All right. Oh, these are yellow atoms. There's 4 of them, and they all stay together. All right. It's an element. It's actually a representation of phosphorus, which exists as 4 atoms of phosphorus stuck together, and they stay together in these little pyramid shapes. Some molecules are really complex. Our protein molecules have hundreds and hundreds of atoms in them. All right, so they can be very small, they can be very big, but it's a molecule. They're staying together. It's pretty stable. Right. Now we can actually talk about 2 classes of pure substances. We can talk about elements, and those are pure substances that contain only one type of atom. All right, and there's about 90 of them that occur naturally. They can be just single atoms together. They could be 2 atoms joined together in molecules, but they can't be broken down into anything simpler. All right, you can't get simpler than one kind of atom. All right, so I've got a picture of silicon on the left. I've got in the glass container, it's a picture of chlorine gas, which has that yellowish greenish color. There are about 118 different elements that are in the modern periodic table. About 90 of those occur naturally. Some are created synthetically. Okay. We can also talk about compounds. So we have our elements, which contain only one kind of element or one kind of atom. And we have our compounds, which contain only one type of molecule. But to be a compound, the molecules must contain two or different kinds of atoms. So that's what I'm showing in the picture model here, right? One pink with one purple. They can be broken down into simpler substances. We can do chemical reactions and break the purple and the pink atoms apart, and that would make them just two elements. So let's do some true false. Let's do some practice and see how we're doing with this. So I'm going to pose a question, pause, think of your answer, and then we'll go on and check. A sample of elemental matter can be broken down into simpler substances. True or false? The answer? It's false. There's only one kind of substance there, and we can't do anything more. A molecule must contain two different kinds of atoms. True or false? Think about it for a second. The answer? It's false. Right? I can have a molecule that contains two of the same kind of atom or two or more different kinds of atoms. That's okay. A compound must contain at least two different kinds of atoms. True or false? The answer is true. Right? For it to be a compound, there must be at least two different kinds of atoms. I can have more than two kinds of atoms, but I must have two different kinds of atoms at a minimum. All right. Let's go on and talk about mixtures. So we talked about our pure substances, which contain only one kind of particle. Mixtures have two or more different substances mixed together physically. All right. A lot of our foods are mixtures. Our air is a mixture. We're giant bags of mixtures. All right. Mixtures are around us and they're very, very common. All right. One of the hallmarks of a mixture is that you can separate the components. All right. You can actually separate them out. In the food pictures I had, you could just pick them out. But we might use filtration. Like if you think about making coffee, right? You're separating the coffee grounds from the liquid. We can use fancy apparatus to do distillation. We can do chromatography to separate the components and separate the colors in the ink pigments. All right. But one of the hallmarks of a mixture is that we can separate the components. The other thing about a mixture is that, the sort of the recipe, the ratio of the different components of the mixture can vary as well. All right, we can have homogeneous mixtures. And what I mean by a homogeneous mixture is that the components of the mixture pretty much have the same ratio no matter where you look in the sample. The word solution is a synonym for a homogeneous mixture. All right, so that's what I'm trying to represent here. I've got green atoms, I've got yellow molecules that are diatomic, but no matter where I look in the sample, the ratio of yellow molecules to green atoms is pretty much the same. Now, it's not perfect because it's a very small sample, but overall, it's pretty much uniform. All right. One thing I do want to point out with the word solution or with homogeneous mixtures, solutions can be solids or liquids or gases. We tend to think of just liquids when we hear the word solution, but that's not a requirement. Solutions can be in any state of matter. All right. So you may have heard of alloys, which are homogeneous mixtures of metals, and many of them are solids. All right. So stainless steel and 18 karat gold and brass are all alloys of different metals in the solid phase. All right. But they're also homogeneous mixtures. All right. Because the ratio is pretty much the same throughout the sample. All right. We can also have heterogeneous mixtures. And what I mean by a heterogeneous mixture is that the ratio of the components varies as you go from one part of the sample to the other. That's what I'm trying to show with my particle level models here. So we see a distinct clump of red particles surrounded by a bunch of gray particles. I have a bunch of yellow particles surrounded by a bunch of white and yellow water molecules, or white and red, water molecules. All right. I see distinct phases. If I look at the left-hand side versus the right-hand side, my ratio of red to gray, or my ratio of water molecules to yellow is different. All right. And it's a heterogeneous mixture. The sample of granite here is a heterogeneous mixture, right? That we've got that non-uniform distribution. And so what we might see is that the ratios of the components vary as you move throughout the sample. And we may even see distinct phases or an interface. Like you can draw outlines around the different colored regions of the granite. So let's do a little practice. All right. So I'm going to have 4 different samples, and I want you to think about, is it a pure substance or a mixture? Are they elements or compounds? Are the mixtures homogeneous or heterogeneous? All right. So we can classify this. Let's look at our first example. All right. So I'm looking at this and I see one type of particle. I see a molecule. I see a molecule that is a compound. Okay. Because I've got the distinct little pieces have one gray and two red components to it, but they're all the same. So it is a pure substance that is a compound. Let's look at the next example. All right. In this sample, I see yellow and I see green. So I've got two different kinds of particles. So this must be a mixture. It's a little hard to say if it's homogeneous or heterogeneous because I've got such a small sample. It does look like there's a little bit of a green cluster and a little bit of a yellow cluster. I'd like to see more of it before I decide. So I'm leaning towards heterogeneous. But I also see that the yellow ones are single atoms and the green ones are two green atoms joined together in molecules, but they're both elements. So it's a mixture of two elements. Let's go on and look at the next picture. All right, definitely have a mixture here. I've got water molecules on the top, those red and white molecules, and then I've got green and white molecules on the bottom. There's a distinct interphase between them. So I think that this is a heterogeneous mixture of two compounds. And then let's do one more. All right, in this, I only see little purple spheres. I don't see any other kinds of particles, so I'm going to go with this being a pure substance of an element. All right, that sounds good. True or false? The picture shows a mixture of two compounds. Well, I see pink and green molecules, and then I see pink molecules. So I think it's a mixture, but I don't think it's a mixture of two compounds. I think it's false. All right, it is a mixture of an element with a compound. Let's see. The picture illustrates a heterogeneous mixture. True or false? So I see blue dots and I see green dots. So it's a mixture, yes. Is it a heterogeneous mixture? Well, I see a big green cluster in the middle surrounded by blue. So I'm going to go with yes. This is a heterogeneous mixture. Sounds good. All right, and that's true. All right, so I think this is a really good stopping point, and we're going to end here. We will talk more about particle level models for classification of matter. It's a really important topic for all chemistry students. It's important that you know the definitions, but also that you can interpret the particle level diagrams. All right, like I said, we're going to stop here. Great.